Hello everyone, I want to talk about today the fractional composition of acids. We know that for an acid, some of it will dissociate, some of it will not dissociate. And if we have diprotic, triprotic, tetraprotic, into the other otic acids, right? Not all of it's going to dissociate. We're going to have different amounts of each. And we can describe that through what we call fractional composition of an acid. So we're going to prove the first, just a monoprotic acid, the fractions of those. And then we're going to look at the formula for if you have any of the acids, and then we'll also prove a diprotic acid, just to be thorough, to show you that this works. So let's assume we have some acid, HA, right, where this H refers to a acidic proton on that acid, and A is the conjugate, it would dissociate in the conjugate base, but it's the carrier of that acidic proton. So we have H, and then we have that other part A, okay, and that will dissociate into H plus and A minus, and there's some Ka associated with that. For right now, since there's only one Ka, we'll just call it Ka, but when we get into polyprotic systems, that's going to become K1, K2, K3. We're going to have multiple Ka values. So let's define the what Ka is equal to. We know that Ka is equal to H plus times A minus all over the concentration of HA. Okay, hopefully that's not too hard to see. And we're actually going to use this. And where we get fractional composition from, where we get this composition from that we'll see, is going to come from the mass balance. Hopefully you are familiar with the mass balance. It just says, okay, for all the acid I add in, the formal concentration of all the acid at equilibrium and all the species of the acid can be described as the formal concentration, F, is equal to the molarity of the undissociated acid plus the concentration of the conjugate base right there, A minus. Okay, so hopefully this isn't too hard to follow so far, but now we're gonna just try and ramp things up here. We're gonna make a couple substitutions to this. And I guess it would be helpful to understand what actually fractional composition is. We're gonna have I'm gonna write this in A. What we're trying to find at the end of the day is alpha A minus and alpha HA. And it's just a fraction and their magnitude is gonna be 0 through 1, and it's gonna tell us, okay, what fraction of HA is the undissociated product? How much of the acid species is HA? Okay, what's that fraction? It's gonna be 0 through 1, it's a ratio. A minus is gonna be a similar idea, but with the conjugate base, okay? How much of that acid species is in the form of A minus? That's gonna be the fraction of A minus, okay? And we're gonna define these to be, hopefully it's a little intuitive. For the fraction of HA, it's gonna be HA over F, which F is the formal concentration, the amount that you put in, right? So it's just the fraction of that. And then conjugate base over F is going to be the fraction of A minus, okay? And these respectively are going to be 0 through 1, but there's an important note to make that the two, when added together, will always equal 1, right? Because if the formal concentration is going to be some number, and it's comprised of the acid plus the conjugate base, well, we know that these two, the magnitudes of these two will equal that when added together. So this should always equate to 1. And if it doesn't, you did something wrong. Well, let's continue our proof here. So we have this mass balance. Now, let's find a different way to express a minus so we can find the fraction of HA. So what I'm trying to find is this guy. Okay, we're going to find this. You have to find them both respectively in this proof. So let's solve for a minus in the Ka, and this will reveal something to us. So we know that Ka times HA equals H plus times A minus. Now, realize all I did was multiply over the HA on both sides. Now divide by H plus and you'll get something that will give you A minus. So, Ka times HA all over H plus, that will give you A minus. So all we're doing is we're basically manipulating the K expression, the equilibrium expression for a simple monoprotic weak acid. Okay? Now, let's substitute this A minus with all this stuff. We're basically reducing the level of unknowns by 1 here by doing this. So F equals HA plus KAHA all over H plus. Now, it's not going to look really intuitive at first, but we can actually solve for the fraction of HA here. We have an F and we have an HA. We just need to get it in terms of HA over F, all right? Or the amount of undissociated acid over the formal concentration, the amount that we added, okay? So let's go ahead and do that. I want to make sure that you guys can see here. You can. So what we need to do first is multiply by the H plus, right, to get rid of the denominator that's kind of causing issues. So let's just call this H plus times F equals H plus HA plus KAHA. Now, hopefully you know a little bit of math. We can factor out an HA on this side, so let's go ahead and do that. I'm gonna try and, I notice whenever I write on the board, it slants down. I'm gonna try and keep it flat. Let's see how good I do. Equals HA, and then that's gonna be multiplied by H plus KA. So do you see how that works? Pretty neat. And what we're going to notice is going to be something very, very, very interesting. If we divide by this and divide by F, we're going to get the fraction of HA. So let's go ahead and do this here. Let's only do this step, the dividing over of just one. So let's say H plus over H plus Ka times F equals HA. Okay, hopefully you can follow that. And now just divide by F, okay, on this side. And you're going to get an expression, okay? This is the expression we have. This is equal to the fraction of dissociation for our undissociated weak monoprotic acid, right? That's going to be what we wanted to find here. This was the first key that we wanted to find. So we found it to be HA over F, which is equal to H plus over H plus Ka. This is actually going to be kind of interesting when we want to determine the trend of what the fraction of dissociation is for like if we have a hexaprotic acid, right? 6 acidic protons. What in the world is happening there? We're going to find a trend that will make this a lot easier, but it's not easy to see now. Okay, so let's now try and find this guy. Okay, let's find the fraction of A minus, okay? And to do this, let's do the same thing we did here. I'm actually going to simplify this by erasing some work so I have a little bit of room. We're going to say H plus over H plus Ka. Now, the way that a lot of people are presented this stuff is they'll say, okay, or they're shown the trend, or they're shown that, and they're just told, okay, go with that. But it's stupid. You have to understand where it's coming from. It's not hard. You need to know the mass balance and the Ka, but that's it, right? It's not terribly difficult to understand. Okay, I want to continue now. Like I said, we're going to be finding the fraction of the fraction of the conjugate base A minus, right? How much of that do we have in there compared to HA, or compared to the formal concentration, I should say. Okay, so let's go ahead and do that. So we're going to come back to here, okay? So you kind of, for all these different forms, you just kind of branch off from the mass balance. Okay, let's redefine this Ka. Now let's solve for HA. It's actually really simple. Multiply HA over, divide by Ka. And hopefully you'll see they kind of just swap positions here. So hopefully you see that you just switch the positions, right? Multiply by HA, divide by Ka, you get this expression. Okay, now all we got to do is substitute. So let's go ahead and do that. So hopefully you notice now we've reduced the number of unknowns by 1, and we have A minus variables in there. We also have an H plus variable, which we probably wouldn't know. But this is going to help us immensely, right? When we want to find the fraction of A minus, we don't want to include HA in there, okay? Because it will make the equation get messy. One will depend on the other, just messy. So we're going to try and get rid of the HA, and that's what we did there. Okay, kind of a similar idea. Remember how in the last one, when we substitute for this, we add over H plus. Now we have over Ka, so let's multiply that out to every term. So F times Ka equals H plus A minus plus A minus Ka. Hopefully that's not too terrible to see. Should be kind of intuitive, I hope. But anywho, let's now factor out. It's literally the same process as last time. Factor out the A minus. This becomes H plus Ka. Okay? So hopefully you can see that. We are going to divide by F on this side and divide by H plus Ka on this side. So we're going to say Ka over H plus Ka equals A minus over F. Okay, notice what we got here when we did all of the math, right? It's not hard math, it's just algebra. We get A minus over F equal to a term of Ka's and H pluses, and it's equal to the fraction of the conjugate base. Okay, so now we did the similar process for this one. It's just now in terms of A minus. So now let's write that out. H plus Ka. Okay? So we got two terms, right? The sum of these will equal 1, and it basically tells you, all this tells you is how much of the, what's the fraction out of 1, what is the fraction that is the undissociated monoprotic acid. Okay, and then what is the fraction of A minus, or the conjugate base? What's the fraction of that out of 1? Right? It relates the two and tells you, okay, what's the rough estimate of how much I have? So I want to give you a little example here of how this might be used. Just quick, we're gonna use these formulas to find the fractions of some acids. So, oh my gosh, this thing does not want to erase. Holy mackerel. So let's assume we have some acid. Let's say Let's actually just use this. I'm not going to point to a real acid because I can't think of any pKa's off the top of my head. I apologize. Let's say that there's some hypothetical acid with a pH of 4. So when you put it in pure water, pure H2O, deionized water, you're going to get a pH of 4. And let's assume that the Ka of this acid is 7.82 times 10 to the negative 3. Okay, what is the fraction of HA, right, the undissociated acid, and what is the fraction of A minus? Okay, so this is hypothetical at most, and I just want you to find these fractions given what you have. And prove that the fractions work because of the relationship of the fractions equaling 1 when you add them. Okay, so hopefully you paused the video, you tried to work through it. We're just going to take these formulas, we've already derived them, let's just use it now. So the fraction of HA is going to be equal to, we actually need to find the concentration of H plus first. And you could actually do this a little bit easier, although the pH might not actually equal to K, so never mind on that idea. The pH is 4, so the H plus concentration is 1.0 times 10 to the negative 4. You would take 10 to the negative 4, which turns out to that. So this fraction of HA, the weak acid, we're going to say is 1.0 times 10 to the negative 4 over 1.0 times 10 to the negative 4 plus 7.82 times 10 to the negative 3. All right, and we'll do a similar thing for the conjugate base, but in this case we have 7.82 times 10 to the negative 3 all over 1.0 times 10 to the negative 4 plus 7.82 times 10 to the negative 3. Notice this adds to whatever that would add to in both terms. So it's some amount, you can think of it as like F, right? The formal amount, right? And then we have each component on the numerator, right? So this will always add to 1 just based off of sight reading the math. That might have been helpful, I'm not too sure. But when we grab a calculator, let's calculate these respectively. So the fraction of the weak acid is 1.0 times 10 to the negative 4, 1.0 times 10 to the negative 4, plus 7.82 times 10 to the negative 3. We're going to find that this fraction is very dilute. All right, and let's also find of A minus. So when we do that, we're going to find 0.987. Okay? When you add these, they do actually add, and I should probably sum that up to 3, right? I'm going to sum it up to 3 just so you can see that it adds to 1. But what this tells you is a lot of the acids form, the formal concentration of the acid, okay, the species that is most prevalent is A minus. The most prevalent, the second most prevalent species, or the least prevalent species, is HA, right? And it tells you how much of each you have relative to the formal concentration. So it's all relative. Hopefully this was a little intuitive to follow. Now I want to get into, okay, what if you have polyprotic systems, right? More than one acidic proton. Okay, so take a screenshot if you want. I don't really care. I'm gonna literally erase everything right now. So if you needed notes, rewind or do whatever you need. This eraser is just terrible. Oh my gosh, it doesn't erase anything. What's the point of being an eraser if you can't erase anything? I mean, like, come on. Stupid eraser. Okay, so let's just take a triprotic acid. H3A is governed by Ka1 into H2A. I'm going to omit the hydrogens. I apologize. And then they're going to go to H, and sorry, this should be a minus. Actually, let's give this guy a plus, so then therefore this guy is just a neutral. And then this guy, H2A's dissociation is governed by Ka2, so let's now call this HA minus. And then we're going to get our final, our conjugate base, you could say, right? The final conjugate base, A2 minus. And that's governed by Ka3. Okay, so hopefully you can see the system here. There's a acid with 3 acidic protons into a diprotic acid, into a monoprotic acid, into a weak, probably weak conjugate base. Okay, so the way that we can find the fractions of every species, so what's the fraction of H3A? What's the fraction of H2A? What is the fraction of HA? What is the fraction of that final weak conjugate base? Okay, that's the question we're seeking to answer. Okay, what are all of these fractions? How could we find it? Well, you can define them in terms of, if you know the pH, you know the H plus concentration, that's the one thing you need, but you also need to know all your Ka values. If you know that, you're good to go. So, the fraction of H3A is defined as, in the numerator we're going to have H plus to the third, and then we're going to have H plus to the third plus H plus squared Ka1. And this is going to get quite lengthy, so maybe omit the numerator, do the denominator, and then center H plus to the third, because we like things nice and neat, right? And then it's going to be H plus Ka1, Ka2, and then plus Ka1, Ka2, Ka3. That is literally how you calculate, and I want to make sure that didn't just get cut off. Okay, so you can see it. That is the fraction of H3A. That is crazy. I mean, that is a huge thing to want to find. So if you were doing this in Excel, I would call this denominator some constant D, and define it as something that you can do, you know, in your spreadsheet. We're actually going to find that this denominator stays the same for all of your fractions. Okay, we actually, in most textbooks, they just denote it D, and then they'll say, okay, D is equal to all this, but I'm actually going to draw it out so you can see it. But just know the denominator stays the same. We're actually going to develop our overall equation from that. And you can verify this with our first one. We found it to be H plus Ka1, right? And we're going to get to the overall formula later, but I'm just kind of getting through all the hard math quick. We'll define the numerator in the second fraction for the second acidic species, right? We gave a proton, now we're at this guy. We're going to say this is H plus squared Ka1. Now let's say, okay, all of that crap on the denominator, right? Literally the exact same as up there, so I'm not going to write it out. We could also talk about the fraction of just HA, okay? And hopefully you can start to see the trend here. We're going to say H plus Ka1, Ka2 over all that denominator junk that we defined here and here. Okay, final guy, it's going to be Ka1, Ka2, Ka3 over all that denominator junk. So I won't even use all this, but all that denominator junk is literally all of that, and I just don't feel like writing it all out, okay? So that's how you find every respective fraction, and notice there's no H2A molarities in those formulas. So there's no H3A plus, and there's no HA or conjugate base in there. So please notice the value in this. All you need to know is the pH and the Kas. That's all you have to know. And you can find out all the fractions of each at a specific pH, right? So kind of helpful. Okay, so let's give the general formula for some acid, any acid. I just wanted to show you a complex example of how we find all the fractions. Hopefully it wasn't too confusing. But the general overall formula would be written like this. So let's say, and this is going to get very like calculus 2y if you remember series. And if you took calculus 2, you probably remember series and like all the n minus stuff. This is where I'm going to kind of pull from that. Let's say we have an acid with n number of acidic hydrogens, where n is some number of those hydrogens. So it could be 3, 6, 1, 2, 50, doesn't matter. It will dissociate by Kn, right? And then we're going to have Hn minus 1a. And then it's going to dissociate Hn minus 2a. And then dot, 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 then we're going to get A, and then there's probably going to be some charge on that acid, but we're not going to be so particular about the charge, right? Because it's not, some formulas are derived from the charge balance, others are from the mass balance. This one's from mass balance, so we don't really care about the charge so much. So please notice, and these K's are going to be Kn minus 1, and then this is going to be Kn minus n, okay? So it gets very messy. But the way that we can describe these fractions, let's say we want to find the fraction of Hna. Well, we're going to say that the numerator is equal to H plus to the nth power. Okay, and the denominator gets very, very tricky. So I'm actually going to define the denominator in our own little function. So the denominator follows this pattern. You're going to have your H plus to the nth degree. Then we're going to follow it with adding H plus n minus 1 Kn. Then we're going to follow that denominator, or sorry, we're going to continue the pattern here. H plus n minus 2, Kn minus 1. Or sorry, it should be K plus 1, right? Because usually we go K1, K2, K3, K4, K5, right? This is n plus n. And then you would keep going forever and ever and ever and ever and ever. And then you'd get to Kn times Kn plus 1 times Kn plus 2 dot 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 times Kn plus n. Okay, so it gets very, very, very tedious when you have 7 or 8. I would honestly just put this all into a spreadsheet, define it once, and just get all your fractions by like a neat spreadsheet that does all the math for you, right? This would blow my mind. So for the nth, the most protonated form of that acid is going to be H plus to the n over D, where we define D to be this trend here. Okay, and then Hn minus 1a is going to be equal to H plus n minus 1 Kn over D. And you're going to keep going following a pattern where we add on the next respective k and we subtract 1 from the power. So please listen, this is very important. For the trend, in the numerator, the d is really easy. You just take the acid, or the h plus to the nth degree, and then add it to 1 degree less than the nth degree times the first ka, and then add it to minus another degree, same kn. Oh, sorry, I made a mistake here. This should be kn, multiplied by kn there as well. Kn never goes away, unfortunately. And we keep going until we get no more nth degree h pluses, and it's just kn plus 1, kn plus 2, ... times kn plus n. So let's define the last one here. Because we'll skip h. Actually, why not? Let's throw it in. hn minus 2a equals h plus n minus 2 kn times kn minus 1. Sorry, this should be plus 1 over d. So hopefully the trend is like awfully clear for you now. I hope that you can see the idea of fractional compositions, and if you wanted to, you could prove this, although, God, this would be very mathy to prove the nth degree one. I think it's more intuitive to follow, okay, prove a monoprotic, maybe prove a diprotic, okay, and then just follow the trend as it's given to you. Because you can find the trend if you just, you do the monoprotic, diprotic, triprotic, tetraprotic, right? Just follow it, and you'll see this works out every single time. So that's how you find the fractions of some acids. I hope you guys enjoyed this video. If you did, please drop a like, comment, and subscribe. I would greatly appreciate it. I have like the worst headache right now, so I am going home. I'm making some mac and cheese. Probably gonna just sit down and rest for a little bit. But stay curious. Chemistry is awesome. Never forget why you're doing chemistry, because it's freaking amazing. Like what's even the point of this? Maybe you got to do that in grad school. Who knows? Just stay awesome, stay curious, have a wonderful day. Bye-bye.